So throughout all this time, we have learned about group theory, where it is a set along with one binary operation. But from today onwards, we will learn about a new concept, that is ring theory. Ring theory, it is like a generalization of the things that you know. Okay, you will see in groups we have one operation, but in ring theory, in rings, we will be having two operations. But before going into that, okay, let us have a look at some examples. Okay, so just consider this set of integers z. Okay, consider the set of integers z along with the two binary operations, plus and dot. Okay, again I repeat, over here, even though we are using plus, but it may not be plus, it may be some other operation. And similarly for multiplication, it may be some other operation other than multiplication. But for simplicity, okay, we are denoting it with plus and also with dot. So let us see, if we have the set of integers, remember that we are now in the set of integers, what are the properties that plus satisfy? Okay, you have this property 1. If a and b, a, b and c, they are all integers, what do we have? We have that a plus b is also an integer, right? If a is an integer, b is an integer, then a plus b is also an integer. Similarly, we have this condition number 2, a plus b plus c is equal to a plus b plus c. Okay, and also we have this integer 0. Okay, like we did in groups, that a plus 0 equal a equal 0 plus a. Since over here we are having two operations, plus and multiplication, so it is best if we specify what is 0. 0 is the additive identity. We will no longer just call it the identity, we will call it the additive identity. Similarly, there exists an integer minus a satisfying a plus minus a equal minus a plus a. That is, minus a is the additive inverse of a. Again, over here, because we are having two operations, plus and multiply, it is best if we specify whether it is an additive inverse or a multiplicative inverse. And over here we also have the fifth property, that is a plus b equal b plus a. Remember that we are in the set of integers, so this also is satisfied. And also, what do we have in this set of integers? These are the properties of dot. Over here, as you see, I've continued 1 up to 5. 1 up to 5, they are the properties for plus. 6 onwards, they are the properties of multiplication. So if a is an integer, b is an integer, if you multiply two integers, it is an integer. So property 6, it holds. Property number 7, as you can see, it holds. Okay, you know that a dot b dot c, it's equal to this. And similarly, you know these two properties. Okay, this one, if you have to say a name for this, it is associative property with respect to multiplication. This one is the associative property with respect to plus. Property number 8, it is the distributive property. Similarly, number 9, distributive property. The only difference is over here a is in the left hand side. Okay, the one outside the bracket is on the left hand side, whereas over here the one outside the bracket, it is in the right hand side. So property 8 and property 9, they are the distributive property. And property number 10, you already know, we have also this integer 1 satisfying a dot 1 equal a equal 1 dot a. Okay, that is an integer. But one thing that we should note is this. Okay, you see here, you have an additive inverse, right? For example, the additive inverse of 1, it is minus 1. The additive inverse of 2, it is minus 2, right? but we did not say anything about multiplicative inverse. We never said that it should have a multiplicative inverse. Let us check. What is the multiplicative inverse of 1? 1 times how much is equal to the multiplicative identity? 1 times 1, right? So 1, it is the multiplicative inverse of 1. What is the multiplicative inverse of minus 1? Minus 1 is still an integer. Again, minus 1. Okay, what is the multiplicative inverse of 2? 2 times how much is equal to 1? 2 times how much is equal to the multiplicative identity? If we have to find the multiplicative inverse, remember, like we were doing in groups, we have to equate it with the multiplicative identity. So 2 times how much is equal to 1? You know this, it is 1 by 2. But you should be very careful. 1 by 2, it is not an integer. It is a rational number, but it is not an integer. That is why if you see all these 10 properties, there is no mention of every element must have a multiplicative inverse. You do not see that. You see property number 4, it says there exists an additive inverse, but you don't see any property that says that every element must have a multiplicative inverse. So this is the property of integers with respect to plus and with respect to multiplication. Now let's see. So like I said, what we are doing in rings, we are trying to generalize things that we know. Okay, so we know the properties of integers with respect to plus and with respect to dot. Similarly, we will do it with any set. So consider any set R with 2 binary operations. I think I should mention this, with 2 binary operations plus and dot, along with the properties that for any a, b, and c belongs to R. Now R is any set. It is no longer just a set of integers. It can be anything. A plus b is an element of R. Okay, we have the same property. Okay, just like we did with the integers. Again, every element must have the additive inverse. It must have an additive identity. It is associative. If you add 2 elements of R, the result will also be an element of R. And also a plus b is equal to b plus a, property number 5. And also property number 6, we have this: if you multiply 2 elements of R, the result, that is a dot b, will also be an element of R. Associative with respect to multiplication. Distributive, again another distributive property, and it must have a multiplicative identity, right? 1. So if you have a set along with these 2 operations and it satisfies both the properties of plus and the properties of multiplication that are listed over here, we will call that set a ring. Okay, so the only example that the example that we are having now is of course the set of integers. The set of integers satisfies all the properties, so that is why we will say that if you have to give an example, we will say that z plus dot is a ring. Okay, it is a ring because all the 10 properties, it is satisfied. One thing that I should mention over here is this. Okay, before, okay, this condition 10 was not considered to be compulsory, but in the modern definition of rings, okay, this condition number 10, it is compulsory. Okay, that is, it should have a multiplicative identity. Before, when we were talking about rings, okay, back when they were first discovered, this condition that it must have a multiplicative identity, it was not so much needed, but now it is compulsory. Okay, so if you analyze the properties of plus and properties of dot, what can you say? These 5 properties, okay, just take a look at these 4 properties first. These 4 properties 1, 2, 3, and 4, they say that R, right, R with respect to plus, it is a group. It is a group because all the 4 properties of a group, they are satisfied with respect to plus. If you combine it with the 5th property, you can say that R is an abelian group with respect to addition. Okay, so keep that in mind. R is an abelian group with respect to addition. So I will write it down. So if you analyze, you can say R is an abelian group with respect to plus. Okay, but with respect to multiplication, it may not be, it is in fact not a group. Okay, as you see, the multiplicative inverse may not exist. The additive inverse exists, but the multiplicative inverse does not exist. So you should note that down. R dot R and dot. Okay, if you take only one operation, that is R, along with multiplication, it may or it may not be a group. I hope that is clear. Okay, so right now, okay, we will be happy with that one example, but of course, maybe by the end of this lecture, we will also learn about more examples. So the first example that we have learned is integers with respect to plus and dot. It is a ring. Keep that in mind. Okay, so this is the note. R is an abelian group. It may not have a multiplicative inverse. Okay, if it satisfies condition, then the ring is a ring with unity. Okay, just like I said, the modern definition of a ring specifies that it must have a unity, that is, it must have the element 1. But again, about this element 0 and this element 1, okay, they are just symbols. Okay, just like when you are dealing with E, the identity, right? Remember, with matrices, it can be other things. It has to be a matrix. So similarly over here, this 0, it is just a symbol. Sometimes it can behave just like the number 0 that you know, or sometimes it may behave like a 0 matrix. Sometimes it may behave like a 0 polynomial. It depends. Okay, depending on upon the set, this number 0 also changes. Similarly, the number 1. Sometimes this number 1, it is a matrix, okay, where it will no longer have this form. Okay, it will have the form of a matrix. Okay, it may be a polynomial and so on. So you should be very careful. Okay, so before going to examples, okay, I think it is best if we learn some more definitions. Okay, commutative ring. We know what is an abelian group. Okay, an abelian group is in fact much simple because we have only one operation. But now if we have 2 operations, it may be a bit difficult to define commutative. Okay, but we always have this a plus b equal b plus a, right? So in fact it is not difficult. So remember that if we define commutativity of a ring, we define it with respect to multiplication. Okay, because it makes no more sense to define it with respect to plus, because with respect to plus it always holds. So if a ring satisfies this, it will be called a commutative ring. If it does not satisfy, then it will be called a non-commutative ring. I hope that is clear. Again, we won't be going to examples right now. Okay, let us just learn some general properties. Just like you have, okay, if because like I said, okay, these rings, okay, we were first studying about integers. So if you have a is an integer and 0 is an integer, a times 0 will give you 0, right? So similarly in rings also, we expect to have the same thing, that a dot 0 equals 0 for all a belongs to R. Now R is any ring. Okay, so it will satisfy the 10 properties of the ring. Okay, that is abelian group with respect to plus, and also the properties with respect to multiplication. So let's see. remember, okay, whenever you have something like this, okay, the thing that you must have to remember, that you must remember, is first line. If you forget this first line, okay, it looks very easy, okay, 0 plus 0 equals 0, but I can assure you that many of us uh, for, forgot about this, okay, during the exam. Okay, and if you forget this first line, okay, you are done, okay, you can no longer proceed. So let's see, okay, start with 0 plus 0 equal 0. This is true because 0 is the identity with respect to plus. Remember that you operate with it gives you E, right? So over here, because it is the additive identity, so 0 plus 0 is also equal to 0. All right, so this is the reason, since 0 is the identity with respect to plus. So I think the first line is clear. So the next line, what you will do is just multiply from the left side by A. And over here I should also say this, you better be careful, because some of you may do something like this: A dot 0 plus 0 equal 0 dot A in the second line. You have to be very careful about this, okay, because on the left hand side you are multiplying from the left hand side, and on the right hand side you are multiplying A on the right hand side. So you must be very careful, okay. In rings, in groups, if you multiply from the left hand side, multiply it from the left hand side, and if you multiply it from the right hand side, multiply it from the right hand side, just like over here, multiply it from the left. So that's why A is on the left. So I hope that line is also is clear. So, and also next, okay, just use that distributive property. We have the distributive property for a ring, so we can use it. A dot 0 plus A dot 0 equal A dot 0. Now all of these elements, A dot 0, it is an element of R. Again I repeat, now all these elements, A dot 0, A dot 0, A dot 0, they are all elements of the ring R. Okay, so if A is an element of R, we can have an additive inverse, right? Minus A. Similarly, if B is an element of R, we can have minus B as the additive inverse. So similarly, now that A dot 0 is in R, we can have minus A dot 0 as the additive inverse. Okay, so that is what we will do. Okay, because the additive inverse always exists, so now we can use that property. Okay, so this is what we are doing. We are subtracting A dot 0, that is adding the additive inverse both sides. This is the additive inverse of A dot 0 on both the sides from the towards the end. Okay, we will have this. So combine this one and this one, you will have 0. Okay, because if A is the additive inverse, you combine it with minus A, you will have 0. Similarly, if minus B is the additive inverse of B, then you will have 0. Similarly for A dot 0, A dot 0 plus minus A dot 0, it will give you 0. So you will have this, right? Okay, so this is what we are having. A dot 0 plus 0 is equal to 0, just like we are having, because 0 is the additive identity, right? A plus 0 will be A from the property, that from the additive identity property. Similarly, B plus 0 is equal to B, so it doesn't matter even if you have A dot 0 plus 0. Okay, this will give you 0. So sorry, A dot 0 plus 0, it will give you A dot 0, and on the right hand side you are having 0, hence you will be having this. I hope that is also clear. And this is property 2. Again, with property 2, you have to remember the first line. Just go through this. The first line is b plus minus b is equal to 0. We have to prove this. Okay, so this is the first line. Multiply by a on both sides. We will have this. Use the distributive property here. You will be having this. A dot 0, we know that it is 0 by property 1. Property 1, it says that a dot 0 equal 0. So that is why a dot 0 equal 0. And also, okay, now I hope this line is also clear. Okay, just subtract minus a dot b from both sides. We will have this. And next, what you will do, combine minus a dot b plus a dot b, you will have 0. So I hope that is also clear, and ultimately we'll have this. Okay, so that is property 2. Property 3, it says that minus a dot minus b minus times minus, it will give you plus. You will have this. Okay, the proof, try it by yourself. Okay, you will have to imagine what first line you will use. Okay, just like over here, the first line that we were using is b plus minus b equals 0. So similarly over here, okay, just think of a first line. Okay, and property number 4, it says that a dot b minus c equal a dot b minus a dot c. Some of you may be thinking, okay, we can do this one in one line. Okay, but in fact we cannot. Okay, because when we were doing about the distributive properties, okay, let us just go back. When we were doing about the distributive properties, let us see. Okay, we were doing the distributive properties only with respect to plus, right? So that is why. But because there is an additive inverse, okay, so this also holds. Okay, the proof goes from this. We cannot do it directly for minus. So first of all, we convert it into a plus minus c. Okay, so then use the distributive property with respect to plus. We'll have this, and also use property number 2. That is, property 2 is this. Okay, and then you will have this. Okay, so this is the proof for property number 4. Again, okay, before going into examples, we will have a look at this special elements in rings. Okay, so we are having, remember I said that every element must have an additive identity. It always exists. The additive identity always exists, but the multiplicative identity, it may or may not exist. So this one, so that is why I mean the multiplicative inverse. The multiplicative inverse, it may or may not exist. So that is why all the elements that have multiplicative inverses will be called invertible elements. A is invertible if there exists A inverse, such that A dot A inverse equal 1. Again, A inverse, it is just a notation. A inverse stands for a single element. Okay, it doesn't mean 1 by A. Always remember, A inverse, it does not mean 1 by A. It is just a notation to denote the inverse of A with respect to multiplication. So again, in the group, because we have only one operation, so that is why the inverse, we were calculating it with respect to that one operation only. But over here, whenever we use this notation A inverse, it always means with respect to multiplication. So I hope that is clear. And also we have 0 divisors. An element of a ring is a 0 divisor if A is unequal to 0. Okay, I will explain why do we need that. Some of you may be confused. Okay, so in number theory, what have you done? In number theory, you are having this. A divides B, right? A divides B, you can write down B equal A x, right? For some integers x. A divides B, you can write it down B equal A x. Now what we are doing over here, we are dividing 0. Okay, so 0 is equal to a times something, okay, which we will denote it with b, or even with x, it doesn't really matter. It is just a notation, a dot b equal 0. So a is the divisor. A is the divisor of 0 if 0 equal a dot b. This first condition is needed because the divisor, it can never be 0. Do not ever divide by 0. That was learned since childhood. Okay, so that is why we need this condition, a unequal to 0, because you cannot divide by 0, but we are dividing 0. Okay, there exists b belongs to R such that a dot b is equal to 0. So I hope that is clear. In the next class, what we will be doing is we will learn about examples. Just keep these definitions in mind. Okay, we will be doing examples of rings. We will also be looking at invertible elements, and also we will be looking at zero divisors. Until then, I think that is enough for today.